In this video, we're going to look at some more applications of L'Hopital's rule. And this time, we're going to do a couple of examples, and these are going to be in the indeterminate form, plus or minus infinity over infinity. And we didn't actually prove this case in the proof in the earlier video, but L'Hopital's rule does work in this case. And notice what you're saying is the numerator and denominator are both going to infinity. And really, what happens with the limit is a matter of which one is approaching infinity the fastest, the rate at which they're approaching infinity. So we're looking at the rates there, which of course the derivatives are the rates of change of the function. So it has something to do with that, as we see from L'Hopital's rule. So it turns out if the absolute value of the numerator function is and the absolute value of the denominator function, if they're growing about the same rate, then ultimately that limit may actually be a real number, and the function may then have an actual limit. On the other hand, if the numerator function, the absolute value, is growing much faster than the denominator function, then the whole thing's going to go towards infinity or possibly negative infinity, or at least from one side or the other. And then if the denominator function is growing much faster than the numerator function, then in fact the whole thing's going to go to zero. So in a way, it's something to do with the relative rates of growth of these things. So, but L'Hopital's rule will apply. So let's do that. Okay. So once again, I'm going to give you a couple functions. You work them out, and then come back and check your work later. Okay, so here's the first one I'd like you to do. Compute the limit as z goes to infinity of natural log of z squared divided by z. Work that one out yourself now. Press pause. So we're trying to find the limit as z goes to infinity of natural log of z squared over z. Now the first thing to do is make sure we can actually use L'Hopital's rule. Notice that if we try to let the bottom go to infinity, z go to infinity, the bottom goes to infinity, the denominator. And the numerator, when we look at it by itself, logarithm function is going to go to infinity as z goes to infinity. Of course, squaring that's just going to make it go to infinity a little bit faster. So, so both the numerator and the denominator functions are going to infinity. And as long as we're talking about pretty large z's, stuff that are bigger than 1, then, well, the whole fraction is defined, and both of the individual functions are continuous and differentiable. So we may apply L'Hopital's rule. L'Hopital's rule says that this limit can be found by just taking the derivative of the top and bottom separately, and then getting taking the limit there. So the derivative of the denominator, the derivative of z with respect to z, is just 1. In the numerator, this is, say, the derivative of u squared, which is 2u times the derivative of u. So that's 2 times natural log of z. The derivative of natural log of z, then, is 1 over z. So we're applying the chain rule there. If we rewrite this is 2 natural log of z over z, and we want to take the limit as z goes to infinity now. So let's look at the form now. Again, the denominator is going to 0, and guess what? Again, the numerator is going to go to 0. So let's take L'Hopital's rule yet again. So with the derivative of the z is 1, and the derivative of the numerator, that's the denominator, the derivative of the numerator is 2 times 1 over z. So this is 2 over z, and of course as z goes to infinity, that fraction is going to go to 0. Let me add one more step here to be very explicit that when we're going from here to the next one, that what we're doing is applying L'Hopital's rule by taking another derivative of the denominator and the numerator separately. Remember, that's how L'Hopital's rule works. So you can see where we applied L'Hopital's rule. And so this says that as z goes to infinity, y goes to 0, so that says the x-axis is a horizontal asymptote on the far right, and here is the graph. It actually is has a vertical asymptote here, comes down, hits the axis, bounces back up, comes up here, and then back down. A little hard to see that on this scale, because what we're interested in is what's happening way out here to the right, and as you can see, it gets closer and closer to the x-axis as we go to the right. Okay, let's try one more. Compute the limit as x goes to 1 from the right side of secant of, no, I don't want secant, I want cotangent. Let me change that. Cotangent of x minus 1 over ln of x minus 1. Let's do that function. Okay? You do it yourself and then come back and check it. Press pause now. Okay? Now you're back. Let's take a look here. This should be the form in minus infinity over minus infinity. We know the graph of cotangent, what it looks like, and we know that if x approaches 1 from the right side, the cotangent graph is going to negative infinity. And of course we know as x approaches 1 from the right side, that's saying it's like the natural logarithm is natural logarithm of, say, u, where u is x minus 1. So that's the log of u as u approaches 0 from the right side. We know that goes to negative infinity. And once again, let me restate that. That's cotangent of u, and the u is approaching 0 from the right side, and cotangent we know approaches negative infinity from that side. So this is the form negative infinity over infinity. As long as we're to the right of 1, both of these numerator and denominator functions are defined and continuous there, and differentiable there even. So now we can apply L'Hopital's rule. So we take the limit as x goes to 1 from the right of the derivative of the top over the derivative of the bottom. Let's see, we'll do the derivative of the bottom first. Derivative log of u is 1 over u times derivative of u. Derivative of x minus 1 is 1. So the denominator now becomes 1 over x minus 1. The numerator, let's see, the derivative cotangent of u is minus cosecant square of u times the derivative of u. The derivative of u is just 1, so we get that. Now, simplifying a bit, I'm going to take the x minus 1, move it to the top, and then also distribute the negative 1, so that becomes minus x and then plus 1, or 1 minus x. The cosecant square I'm going to flip to the bottom and make it just sine square. Now, if I plug in x is 1, I get 1 minus 1 is 0 on the top. 1 minus 1 is 0, and sine of 0 is 0, and 0 squared is 0. So I get the form 0 over 0. So guess what? We can apply L'Hopital's rule again, because again, if we're talking to the right of 1, both these functions are continuous and differentiable there. These two new functions considered separately are continuous and differentiable everywhere. Okay, continuing on, we do the derivative of the top and the bottom. That's what L'Hopital's rule says to do. So the derivative of 1 minus x squared is negative 1. Derivative of sine square of u is 2 sine of, well, let's see, this is like v is sine of x minus 1. So we got the derivative of v squared, so that's 2v times the derivative of v. Oh, that's wrong. Let me see if I can fix that. The conclusion's right, but we got to do the chain rule right here. So this is v is sine of x minus 1. So this is v squared, and so we get 2v times the derivative of v. So we got to do the derivative of sine of x minus 1, which is actually cosine of x minus 1. And then you have to take the derivative of the inside part, which is times another 1. But when you look at this form, as x approaches 1 from the right, both of these guys approach 0. So cosine of 0 approaches 1. This is sine of 0, which is 0. So 2 times 0 times 1 is 0. So the bottom is 0. The top is a constant, negative 1. This approaches negative 1 over 0. And so that's going to approach, at least from one side, it's going to either approach infinity or minus infinity. We just kind of need to look at the sign of it to see what's going to happen. Now, when you're to the right of 1, cosine, then the x minus 1 is to the right, just to the right of 0. So if x is just to the right of 1, x minus 1 is just to the right of 0. Cosine of numbers just to the right of 0 are positive. They're close to 1. Sine of numbers just to the right of 0 are close to 0, but they're positive. And of course, 2 is positive. So everything in the bottom is positive, and the numerator is negative, so the whole thing is negative. So in fact, this must be approaching negative infinity. And L'Hopital's rule does work even when there's not an actual limit, but if you can say that it goes to infinity or minus infinity for this 1 at the end, then you can say the same thing for the 1 at the beginning. So what does this tell us? It tells us if we look at this, at x equals 1 should, at least on the right side of x equals 1, we should have a vertical asymptote, and the graph should be going, as we come from right to left, should be going down towards the asymptote there. So the arrow will be pointing down. Now in this one, in fact, we get that the ln of something must, the argument of the ln, the natural logarithm or any logarithm, any base logarithm, must be strictly positive. So x minus 1 has to be strictly positive. So x has to be strictly greater than 1. So in fact, there was not going to be any graph here to the left of 1. 1 just to the right of 1 is where it actually starts. So here you see the graph. Nothing's over here to the left of 1. You do have a vertical asymptote at 1, which is what we just proved. Okay. Now in the next video, we're going to look at some more examples. These will not, we will not be able to apply L'Hopital's rule directly because they won't be in the form 0 over 0 or infinity over infinity, but rather 0 times infinity. But there's a way to manipulate them so that we can put them in a form, and then we can apply L'Hopital's rule.